When I was first introduced to the concepts of vectors, matrices, something called tensors, as well as something called Bra-Ket notation, which is something used in quantum physics, usually, it was something kind of confusing and obscure to me. I didn't really understand why things followed the rules that they did. I just understood that there were certain rules for how you multiplied these objects with each other. And at first, it wasn't clear why they chose these rules, but I'm going to try to explain how this makes complete sense, and I'm going to use, as an example, counting your change. So, so I'm going to go over some notation in this video first. I'm going to be using these yellow things that point to the right, which are examples of wallets, pennies, dollars. These are called kets, also called a column vector or just a vector. And the bra is the covector or a row vector, and it's the corresponding thing. And then we're going to be considering these counting things. And we're going to have these scalars, which are just numbers, and you're used to how scalars work. We just multiply them by basically a coefficient. And so let's start out. We have a wallet, and it's made up of all these coins and these dollar bills. So these are going to be represented with a dollar, a quarter, dime, and these coin vectors. And having 9 of these is going to be 9 times the penny vector, 7 nickels. So we're going to call this the wallet vector, and this is the sum of all these other things. And we're going to use a pennies counting function, which is a covector. And here we're going to have, we show that the distributive property holds, so you can distribute any multiplication into multiplying it and summing it over and over again. We can also commute any scalar multiplications. And here we're showing that the number of pennies in a penny is 1, and the number of pennies in any of the other basis vectors is 0. And so that all goes to 0 except for the first one, which goes to 1. So it's 1 times 9. So there's 9 pennies. And as we can see, using pennies on this wallet gives us the number of pennies, the same with nickels, dimes, quarters, and dollar bills. So the function of these covectors is to count the number. So here I'm going to introduce something called the number of coins, which is another covector, but it's not a basis covector. It's made of a sum of basis covectors, which are these pennies, nickels, dimes, and quarters. And we're going to have no dollar bills, just coins. And we're going to have one of each. So it's just the addition of pennies, nickels, dimes, and quarters as counting functions. So how many coins are in our wallet? Well, we're going to use the distributive property again. And with each of these, we already calculated 9, 7, 2, and 2. So this is going to be 20. And we can also represent this as the wallet as a column vector, and we can represent all of these basis vectors as row vectors with all zeros except ones, and the number of coins is going to be another row vector. Here we're going to introduce the total cents. The total number of cents in pennies 1, 5 for nickels, 10 for dimes, 25 for quarters, and so on. So how many total cents are in here? We're going to use the distributive property once again, and we're just going to multiply 9 times 1, 7 times 5, and so on. And if you do the math out, you're going to get a value of 414. So hopefully you can see how distributive property works and how this gives us the inner product idea. So that explains inner products, which, as we say, are a covector in front of a vector. The outer product is a vector in front of a covector, or a ket bra instead of the bra ket, which is the inner product. So here I'm going to show if you have the dime vector in front of the penny covector, you turn 2 pennies into 2 dimes. Every penny gets turned into a dime, and you can see that the scalars commute with both of these things, and then you have a penny counting how many pennies in a penny, and that goes to one. So that's an introduction to the basic idea of this ket broad and what it does. I'm going to move on from coins to permutation. So a permutation takes the first element and brings it to a third element. In general, permutations change the order, but here it's 1 to 3, 2 to 1, and 3 to 2, and that's represented by these ket bras. You can also think of these as the column vector times a row vector, which is a matrix with all zeros except one somewhere. These are also matrices which can be expressed as a product of smaller ket bras. One of the questions of matrices is whether your matrix can be factored essentially into these things, and that's called being a singular matrix. And it's irreversible as an operation essentially. I'm just going to show you about how you can use this formulation of thinking of these matrices as an algebraic sum of ket bras, and how that can be used to just use the distributive property to explain how matrix multiplication works. It is a bit of a difficult work, especially when I'm drawing out these things. It's extra symbols. There might be a simpler symbol, but if you watch some of the algebra I'm doing, it shows how, with the permutation, how that works. In general, matrices are sums of ket bras times a scale factor, so permutations only have zeros and ones, and there's only one ket for every bra, and so on. However, with a general matrix like these A, B, C, D, and E, F, G, H, 2 by 2 matrices, I'm going to show that you can kind of derive the formula for matrix multiplication using just normal algebra that you're used to, along with these rules about multiplying kets and bras and working with the basis vectors. So what you get from doing the multiplication this way is eventually you have these four basis ket bras of 1, 1, 1, 2. I actually wrote it wrong at first, so I'm going to correct that. But it's 1, 1, 1, 2, 2, 1, and 2, 2. And this ends up with AE plus BG, AF plus BH, CE plus DG, and EF plus DH. And the point I want to stress here is just that matrix multiplication is just the distributive property with these ket bras, or also vector covector products, or sums of ket bras at least. All right, so here I'm going to have a final example. I've been talking about these vectors. How you're usually introduced to vectors in vector addition is with this geometric method, and I'm going to bring it back to that. So you can think of these vectors in geometry as sums of an x and y, at least in 2 dimensions, set of vectors. And we're going to think of a rotation matrix as an operation on vectors that takes the x and brings it to y, and takes the y and brings it to negative x. And that's the fundamental thing. We know what happens to both basis vectors, and all vectors can be expressed as a sum of scalars times these basis vectors. So we have yx minus xy describing our rotation matrix. And I'm going to rewrite this as 2 1 minus 1, 2. So it takes 2 to 1 and minus signs that, and it takes 1 to 2. And we can also rewrite this, and we can write this as a 0 minus 1, 1, 0 matrix like normal. But we're going to keep it in the algebraic form and just do the rules and show that we're going to get negative of the identity matrix, which I'm using as this kind of 1. This has been an introduction to a concept that I'd like to elaborate on more in the future, maybe, and talk about maybe tensors and quantum mechanics as well. But for now, this has been kind of a rushed video, so I'm sorry if the quality is kind of poor, but I was hoping to get it out in time for the competition. And hopefully you've learned something, and maybe this will help make matrix multiplication and the idea of vector spaces make more sense to you. That's all for now. Thanks for watching if you watched.